We are Group 7 and we have chosen the book Principles of Distributed Database Systems, Chapter 5, Data and Access Control. I'm Zunaira Khan and I'll be describing the first topic in our chapter, which is view management. So firstly, in this chapter, we will understand and review how the centralized solution to semantic data control is used and the problems associated with distributed environment and the solutions of these. So the cost of enforcing semantic data control is high for resource utilization. And we emphasize the impact of directory management on the performance of semantic data control mechanisms. In a relational system, a view is a virtual relation defined as the result of a query on base relations. A view is a dynamic window that reflects all updates to a database. An important issue within this distributed DBMS is to make view materialization efficient. That is, if users want to access the database through views, they cannot see or manipulate the hidden data. Within views in centralized DBMS, we have logical independence and query modification. So a view is a relation derived from base relations as a result of relational query. Here we have updates through views which are handled automatically only if they are propagated correctly. Because we know that views involve queries with selection, projection, join, aggregate functions, and so on. Mapping a query is expressed on base relations, which can be done using query modification. Next, we have views in distributed DBMS. So current systems are very restrictive about supporting updates through views. The views in a distributed DBMS is derived from fragmented relations stored at different sites. If the view is not present at the site where the query is issued, so remote access to the view definition site is necessary. The mapping of the query is expressed in views through a base relation. And then within this mapping of distributed queries, the qualification that is defining the view is found in distributed database catalog, which is merged with the query to provide that information on a base relation. An alternative solution to this is materialized view. A materialized view stores the tuples of a view like other database tuples, and the access to the materialized view is also much faster. So what is materialized view? It is a copy of some base data, and for this maintenance should be done, which is defined again as the process of updating a materialized view to reflect the changes. It is to specify when and how a view can be refreshed, and it can be refreshed in two modes: immediate and deferred. Within immediate, the biggest advantage is it is always consistent with the base data. However, the transaction time is increased. And deferred is most preferred for practical use, where if the view is refreshed, it is divided into separate transactions. However, the query time is increased. That's all from me. Now we will move on to the next topic, data security. Thank you.
Thank you for inviting me. I'm Mahidatif Hussain and I'll be talking about the data security aspect. It mainly consists of two things, which is data protection and data access. Data protection is achieved by encrypting the data by using an algorithm like Diffie-Hellman. Data access in a centralized database system is maintained in two ways, which is discretion access control and multi-level access control. In the discretion access control, there are three main actors, which are subject, object, and operation. Subject is the user, operation is the SQL statement like select and update, and object is the data. These informations are stored in something called the authorization matrix. It can be stored by row, by column, or by element. By storing by row or column has its own disadvantages, but by element is the most efficient one. But there are some problems with discretionary access control, and to mitigate those, we need multi-level access control. Here there are mainly security levels like top secret, secret, confidential, and unclassified. And in this protocol, there are two main rules which are followed, which are no write-up rule and no read-up rule. According to no read-up rule, subject can only read data from the same or lower level objects, and in no write-up rule, subject at a certain security level can only write same or higher level objects. And to enforce discretion access control and multi-level access control in a distributed system, there are three main solutions. One of them is the first one, which is also called the SSO, in which authorization information is maintained at a central site. The second way is in which authorization information is replicated in all the sites in the catalog, but this has some issues due to synchronization. And in the last solution, all of the sites of uh, DBMS identify and authenticate themselves using something like a site passwords. So in a distributed system, multi-level access control requires a lot of complex logic and extensions. So that's it from my part. Now I would like to invite the next speaker.
Hello, I am Tariq bin Shams. I will describe the semantic integrity control for data and access control chapters. Here is this semantic integrity control. So, uh, another crucial and challenging topic for a database system is how to assure database consistency. A database state is considered to be consistent if the database fulfills a set of requirements called semantic integrity constraints. Maintaining a consistent database involves several mechanisms such as concurrency control, reliability protection, and semantic integrity control, which are supplied as part of transaction management. Semantic integrity control ensures database consistency by rejecting update transactions that lead to conflicting database state. There are two types of semantic integrity constraints. One is centralized and the other one is distributed. Specification of uh, specification of centralized integrity constraints should be controlled by the database administrator using high-level language. For this, they present a declarative language for setting integrity constraints. This language is much in the spirit of normal SQL language, but with additional generality. It allows one to specify read or drop integrity constraints. These restrictions can be defined either at relation formation time or at any time, even if the relation already contains tuple. In all circumstances, though, the syntax is almost the same. For simplicity and without lack of generality, assume that uh, they assume that the result of integrity constraints violation is to avoid the violating transaction. For the time being, integrity reinforcement is concentrating on enforcing semantic integrity, which consists of rejecting update transactions that breach certain integrity constraints when the update state of the database makes a consistent no longer true. A violation has occurred. Developing effective enforcement algorithm is a significant challenging when building an integrity management. Uh, and building an uh, integrity management. So developing effective enforcement algorithm is a significant challenge when building an integrity manager. Two main strategy allowed the rejection of inconsistent update transaction. So now the distributed semantic integrity control. Here, distributed semantic integrity control divides into two parts. One is definition of distributed integration, then the summary of distributed integrity control. Here, some strategies for protecting the data in distributed database from semantic drift. These are expansion of the simplification method outlined previously. In what follows, they presume global transaction management capabilities as offered for homogeneous system or multi-database system. Therefore, the specification and storing of assertion and the enforcement of these constraints are the two key issues in developing an integrity manager for such a distributed DBMS. They we will talk about the challenges of integrity constraints checking, the absence of global transaction support. As a clear definition of distributed integrity constraints tuple relational Calculus is the preferred notation for expressing integrity constants for each tuple in the Cartesian product of the relation established by the tuple variables. Each assertion is interpreted as a query qualification that is either true or false. Since assertion may reference data located in different location, it is important to choose where to keep the constraints in order to cut down on integrity checking expense. Individual constraints, set oriented constraints, and aggregated involved constraints are the three types of integrity constraints that can be distinguished using a taxonomy based technique. So, individual constraints is the constraint definition is sent to all other sites that contain fragments of the relational involved in the constraint. The constraint must be compatible with the relational data at each site. Compatibility can be checked at two levels: predicate and data. Set-oriented constraint. Multivariable joint predicates are used in set-oriented restriction. A pretest is always connected with a single connection. Even if the assertion predicate can span multiple relations, all the sites that host a fragment referenced by this variable can then receive the constraint specification. The relational joint predicate is not the only part of the relational that is checked for compatibility. Compatibility. So now the constraint involve aggregates. Uh, Involving aggregates, these constraints are costly to access since they require calculating aggregate functions such as mean, max, sum, and count are aggregated aggregation function. Each aggregate function includes projection and selection. So now the summary of distributed integrity control. The cost of communication and processing involved in implementing distributed constraints can sometimes be prohibited, which is the primary challenge of distributed integrity control. When developing a distributed integrity manager, the two most important challenges to overcome are the formulation of distributed assertion and the development of enforcement algorithm that reduces the amount of money spent of the distributed integrity checking. In this chapter, we demonstrate that distributed integrity control may be fully achieved by expanding a preventative technique that is based on the compilation of symmetric integrity constraints into pretests. This was done in order to prove the distributed integrity control is absolutely realizable. So that is the access. That is the data and access control chapter. Uh, mm, Thank you.